This second example, we're going to simulate a heat exchanger, okay, but not a simple heat exchanger considering only heating or cooling as we did in the previous example, but now we're going to simulate a heat exchanger considering a rigorous model, okay, so we'll be considering the geometry of the heat exchanger and other aspects and characteristics of this unit operation. Right, and so I prepared here a case study for simulation, and we will be reading and understanding the conditions and the example for next simulating it in Aspen Plus. Okay, so the case study is: in a certain petrochemical industry, a shell and tub heat exchanger is used to heat an 103,000 pounds per hour of naphtha stream at 200 psi from 180 Fahrenheit degree to 210 Fahrenheit degree, and for this purpose a kerosene stream at 225 psi and 320 Fahrenheit degrees with a flow rate of 29,800 pounds per hour is available to be reused later in the process at temperature of at least 220 Fahrenheit degrees. Therefore, what should be the outlet temperature of the kerosene stream, the effective surface area, and the heat transfer coefficient for the heat exchanger in question? Okay, so we are going to specify these conditions for the streams. Okay, and it's also required to check this condition, this constraint for the kerosene stream in the final of our simulation. And next, we have all conditions that will be used in the simulation of this heat exchange. Okay, so and it's also important to say that Aspen use supplement coupled for simulating this kind of heat exchanger. Okay, well, it's called EDR, okay, the exchanger design and rating supplement, in which we can configure for a shell and tub heat exchanger the shell type, the number of shell passes, the tub passes per shell, the shell diameter, the tub pitch, number of tubs in the shell and tub heat exchanger, the fouling in the shell, the conditions of tub length, the tub fouling, the diameter and inner and outer diameters for the tubs, and the type of the tubs, conditions for the baffles, okay, which are used in the heat exchanger for promoting this kind of simulation. And now we need to configure the pressure drop allowable, if you have pressure drop, to check that the geometry it's enough, it's sufficient for promoting the heat exchanger that you want to implement in this case study. Okay, our strings of naphtha and kerosene will be considered here as a mixture of these compounds. Okay, so naphtha has 3 compounds and kerosene has here I think 12 compounds with these mass fractions, and we need to select all the compounds for our simulation. And as we are going to simulate strings with petrochemical compounds, we'll be considering using the Peng-Robinson model for thermodynamic properties and phase equilibrium. Okay, so these are the conditions that we are going to define in our simulation. So first, let's define the compounds, the thermodynamic package, and next we're going to the simulation for creating this heat exchanger, shell and tub heat exchanger for simulating it. Okay, so let's go to Aspen Plus next. So initially, let's find all the compounds for our simulation. Okay, I think we are going to use for naphtha configuration. Let's find NO9 as the first compound. Let's find it here, this one. After that, let's find cyclooctane. Is this one. After benzene, that are the compounds for that compound naphtha. Okay, this one only benzene. After that, let's select now the compounds for kerosene. Okay, we are going to find first and decane. And decane here. For the other hydrocarbon, let's find using the number of carbons. Okay, so for undecane, let's try to search considering using NC11. Yes, it was finding here. Always use add, okay, because if you don't, you replace it the previous compound, and that's not what we want. Okay, now the C12, C13, triadecane, C14, C15, and C16. Also, we need to define fluorine. Okay. We have other compounds, other hydrocarbonates. Their names are a little bit different. You have here an abbreviation which use it, and also the Thai-naphtha. Naphthalene, it was not found with this name. Let me check here another possibility. I think an 8 was missing here, maybe. Yes, this one. Let's find the one with naphthalene here. And at last, anthracene. This one. Okay, finally we added all compounds that we'll be using in our simulation for representing the 3 first compounds, for representing naphtha, and the remaining one for representing kerosene. Okay, the methods, as I explained, as all our hydrocarbonates, we will be using Pengy-Robson. And let's click run for checking if you can. Yes, we can estimate all properties for the components used in the simulation. Okay, so let's go next for the flow sheet stage for inserting our heat exchanging in our strings. Now in exchangers, let's select here heat X. Let's insert our, here in this connection is the cold fluid. Okay, so in our case, I think our cold fluid, checking here the example, is the naphtha string. Okay, so the cold fluid here, it enters here and it left the heat exchanger here. Okay, so this is the naphtha string, and the hot fluid here is showing hot required. We are going to insert here the kerosene. Okay, so for representing, I will insert here naphtha in or naphtha in, and here naphtha out. I can't use all characters, so I will insert it here, naphtha out, and after I insert here kerosene, and here I need to represent using, I click in the wrong place. Kerosene, I can't use more characters, so kerosene, out and KIN. Okay, so this is the only way of representing the strings. If you want, you can do different. Okay, I can use the scroll of the mouse for zoom in or zoom out. Okay, and also I will put here heat exchanger. Okay, so I think now we can configure our strings. For configuring our NAFTA strings, their conditions in the problem are that we have here for NAFTA the pressure equivalent to 200 PSI, the temperature at the inlet string is 108 Fahrenheit. Okay, the total mass flow in pounds per hour, let me check it, it is 103,000. Okay, and the mass fractions for the compounds, they are here. For the first three, we have these values in table 1. That summing, it must be equal to 1. Okay, let's check it. We can check here in this space, in this square, the total is equals to 1. So we defined the string for NAFTA in the inlet string. Now let's define the kerosene in. For the kerosene in string, I can select it and inform the conditions. Okay, I will inform the conditions here for temperature at 320 Fahrenheit, pressure equals to 225 PSI, and the mass flow in the basis of mass, in this case pounds per hour. We have a total flow rate equals to 29,800 pounds per hour. Okay, and the mass fraction for defining the composition, we have many compounds. Okay, so I'm here looking for table 1 and I will be inserting all the values from table 1. If you want, you can check that for all hydrocarbons, and here I am defining. I think I jumped at 1 here. Okay, sorry, I'll try to do that, and to apply it here I can use Ctrl+C, Ctrl+X, Ctrl+V. Okay, luckily for inserting the compound that I jumped at here. In this case, yes, perfectly. Here the sum is equals to 1. So we define the input strings, the inlet strings, and now I will save it here. Remember, saving your simulations always, okay, for not having problems with crashing the software or the simulation. So let's go now to configure our heat exchanger. Saving the simulation, remember here in Save As, always select the option Aspen Plus document, okay, because this is the condition that we use for saving all the specifications. If you select your other ones, we will be saving only other configurations, so always select the Aspen Plus document. Okay, so now in the heat exchanger, first we are going to simulate it considering a shortcut model for predicting an initial temperature at the output in the designing mode, and after that we'll pass to the rigorous mode considering here shell and tub for configuring the geometry of the heat exchanger. Okay, in your case the hot fluid or the kerosene stream will be passing the shell, the cold fluid naphtha in the tubs. We will define the output temperature here for the stream outlet temperature for naphtha equals to 210 Fahrenheit degrees. And also let's consider a co-current in the beginning configuration for our case study. Okay, and let's click next here for simulating, and also it predicted the results in the output strings. Okay, we can check here the output strings in Celsius. Okay, but we can change it here for other strings. It is naphtha in, naphtha out to have equivalent 210, in kerosene input to have here the temperature at 320, and the temperature at the output for the kerosene string, it is over 220 as we desired. Okay, so this is the simulation in the shortcut modes, and now we are going to pass for the rigorous mode. Okay, because in the first mode, in the shortcut mode, we are only predicting the area for heat transfer. Okay, if you check here in the results for this heat exchanger, we have here the string results, we have the results in block options, geometry results, thermal results. We have here the heat exchanger, the heat that exchanged between the strings. Okay, have the results for the balance, the energy balance. Exchanger details, we have here the area, the required area for promoting this transfer of energy, and also the global heat transfer coefficient and the log mean temperature difference calculated for this condition. Okay, now let's try to pass for the shell and tub mode. So I will select shell and tub. It will carry the supplement EDR. Okay, and here we'll be sizing our heat exchanger, inserting information that we have about our process. Okay, so let me find here the configuration for our heat exchanger, and let's define all these conditions here next. Okay, we need to inform some conditions for our strings for calculating how the temperature will be determined in all steps of our heat exchanger in the defining geometry. Okay, first I think we need to check here for multiple passes in the shell. Okay, I will select here 2 passes in the shell as was informed in our problem. Okay, and after that let's go to shell and tub again, and here let's specify the options that we have. Okay, the hot fluid is in the shell. We have information here about the number of shell passes. We have information for the pitch. Our pitch is equals to 1. Okay, this is the distance between tubs. The tub output here diameter we have for shell, I think the shell diameter it is in inches. We have here let me check here, is for the shell. Yes, it is 17,25. Okay, I think it is here. No, it's not possible to configure this size. Let's use the standard value for now. Okay, this is the outside diameter for tubs. No, for tubs is this value. Okay, for tubs 0.75. For tub patterning we use 90 square. Okay, it was defined in the problem. Tables are in baffle window. Yes, we have here baffle types. We have vertical baffles. Okay, we also have here the material was not specified. We need to specify here some sizes. For shell diameter we have the value it was 70.25, and the thumb length it was specified in your problem as 16 feet. Okay, so we need to change the units here. The baffle spine sensor to the if it was 3.5. The number of tubs 166. I think it was, or the number of tub passes. No, tub passes is 1. It's not here the number of tubs. The number of tubs, maybe it's next. You need to define later. Shell in series. No, we're not going to define that. I think it is all defined in here. For our configuration of the heat exchanger, I think we need to change here. Okay, we're going to use let me find here. This is the standard, but we are going to be rating, and now yes, we can define here the number of tubs 166. And also we need to define the number of baffles. The number of baffles, I think it was not specified the number, but we have here only the baffles passing. Okay, and it will try to size later through this space here the total tub length and the number of baffles. It will be calculated here. For the process here we have some conditions that we already defined in our strings. Okay, we have here the outlet temperature only for naphtha. Okay, it was defined. We don't define for the outlet temperature. Here we have some information for heat exchange. The allowable pressure drop, it is important. For the tub it was allowed, I think it was allowed 10, right? And for the shell it was allowed 5. The fouling resistance, it was specified at 0 in another unit, I think. Okay, no, it's in this unit. Fouling resistance will be specified at 0.005 for all tub and shell. And also we will calculate the pressure drop here. I think all conditions are specified. Let me check again, and we can try to simulate our heat exchanger for giving the temperature profile along the shell and the tub. Okay, so you can click size. Okay, and when you click size we go to this result of our window in the configuration of the heat exchanger. Okay, and you can see that it calculates or estimates all other parameters for the heat exchanger. Okay, and here we have a draw of our heat exchanger, shell and tub. Here we have the profile for the temperature for the hot fluid here, in this case for kerosene. You can see here that the temperature starts there and down to under 220 that we want, but it's not, so it's close. And here the naphtha is increasing its temperature. Okay, and here we have some options. The tub layout for the number of tubs. We can see here another view for the heat exchanger for checking the configuration to the number of tubs that we specified here. And if you want, you can do it again only changing the number of shells, number of passes. We can try to change here the possibilities or the configurations of the geometry, and when we do that, we can try to size it again. Okay, we only need to run here again and need to estimate the temperature profile in this heat exchanger that we designed here. So we can try to do many cases, try to see the simulation of different layouts of heat exchangers in order to achieve the best option for the geometry. Okay, and if you want, you can change here the values for the project. Okay, if you close it, we can see here this is the size exchanger for changing some configuration here, but we can use this option specify geometry for going back again in this EDR supplement window and change conditions. Okay, if I want to increase or decrease the number of tubs, for example, here I can just change here and run it again, or giving here another condition which is used for this geometry. Okay, and I check here, it's different. And again, in geometry results or thermal results, here I can check the area, I can check the values for a rigorous simulation for heat exchanger. Okay, so I think here we can try many case studies, we can simulate many heat exchangers, and also we can try another kinds of heat exchanger. You can try to use plate if you want, specifying the number of plates, the size of plates. Okay, and you can try to simulate other conditions. Okay, and also of course you can try to use different fluids, and maybe next study design heat exchanger for heat integration in other studies in your research if you want. Okay, so I think that's it in example 2. In this condition here that I simulated last, we can answer that we have more than 220 Fahrenheit degree for simulating the condition for the output temperature for kerosene in this case. Okay, so that's it for example 2. So good luck.